Hey everyone, this is Greg Hendricks. In this video we're going to go over some vector math. I wanted to create this video because there's a lot of resources out there on how to add, subtract vectors, how to calculate the dot cross product and things like that. There's not too many videos on how to actually apply that stuff within Maya. Now I'm going to be showing you how to apply this stuff and create a script with it. So I'm not going to go over the very basics of vector math. So I included a link to two different videos that I recommend you to watch. One's called 3D Math for Artists, and he goes over a lot of the basics of vectors and how to add them and subtract them, what the dot product is, what the cross product is. He goes over something similar we're going to talk about today, but we're going to take it a step further than he did in that video. And the second video is from a series called Cult of Rig. And I included the day 5 video, and he goes over vector math, and I recommend you watch that. So what we're going to demonstrate with the vector math is how to calculate where to place a pole vector control. So if we create a IK handle, rotate plane. Now if we have this plane from this 3-joint chain, and if the control is not on this plane, when you create the pole vector constraint, it's going to make the joint snap and actually rotate. So if we create a locator, and just snap it up here, and move it back, and create the pole vector, you see how it moved, and now it has rotate values, which isn't what we want. And that happens because it's not on the same plane as the joint chain. Now, you can use Maya tricks to figure this out. So for example, you can go to Mesh Tools, create Polygon, and we'll create a triangle here. And I'll hit F9, select this vertex, and hold W key down and left click and hold to bring up the move options, and I'll go down to the bottom left section called axis and change it to normal. And now we can pull this out along the normal. Oops. And snap this here. And now you can tell it's all on the same plane. So if we create, let's create that IK handle again. So now if we create the pole vector, it's not going to snap. And you see the rotate values are still 0. So we're going to figure this out mathematically. And the first thing we're going to do is find the midpoint between this joint and this last joint, and calculate and then push out towards this middle joint. So if I select these two, select the locator, and create a point constraint with maintain offset off, so it snaps right in the middle. And let's shrink this. So basically we're going to find the midpoint, point towards this middle joint, and then we're going to scale out from here and place the pole vector control at the end of this line. But the problem with this technique is if we extend the arm so it's more straight, and then we demonstrate the same thing where we point a line there and scale it out. The more straight the arm gets, the closer this pole vector control is going to get to the wrist. And technically it's on the same plane, so it's not going to make the joints rotate. But as an animator, like, they're not expecting, this isn't a very convenient place to have the pole vector. I expect it like to be out here somewhere. So the more straight the arm gets, the closer this control is going to get to the wrist, which isn't what we want. So we'll just take this step by step and figure out the middle point and figure this out, and then we'll figure out the second problem with we have a more straight arm. So let's open the script editor and let's import maya.commands as commands, and import maya.openMaya. So we're going to use just one thing from the Maya API. It's called the mVector, and it allows us to operate on vectors a lot easier, which you'll see in a few minutes. So first thing we want to do is get the position of each of these joints. And to do that, let's create a variable called root joint position and use xform. And we'll give it the joint name. And we'll query the world space translation. Oops. And we'll do the same for the other two joints. It's the mid joint, end joint, and then we'll create a function to get the pole vector position, and we'll pass in the 3 positions we just queried. So let's fill this out. Okay. So now we got the positions of each joint. Let's create the vectors, the mVectors. So to do that, we'll create new variables and we'll assign it the mVector. And we'll give it the x, y, and z position of each of these. And since it's from a list, it's 0, 1, and 2. And we'll do the same for the mid and end. Alright, so now we got vectors from each of these positions. So what does that exactly mean? Because if you look up online any tutorial about vector math, a vector has a magnitude and a direction. So right now we just give it position. So where's the direction come from? And what happens is when we create a vector and we give it the position coordinates that we just queried, the beginning of the vector is always at the origin. So the root vector we just made is this, the mid vector is this, and the end vector looks like this. So the beginning always starts at the origin, and the end point is position you give it. And let me change these colors. Just red, green, and blue. Alright, so we got 3 vectors, and visually this is what they look like. And we want to get this middle position. So first we're going to get this length from this root to this end joint. And we'll create a variable called midpoint. And then we'll take the end joint vector and subtract it with the root joint vector. And let's create another function called create locator, or just create loc, and we'll create a location at the position we provide it, because we're going to create locators a bunch of times to test out our calculations. So let's do the space locator command and let's move it. Another useful thing about using the mVector class is you can access each of the x, y, and z components by just doing .x, .y, .z, whereas with xform or using a list, you got to refer to it by the index in the array. So that's another plus to using mVectors. So let's create a locator at this point we just calculated. Alright, so now we have a vector pointing to here. So how exactly did that happen? So we took the end joint and subtracted it from the root joint. So let's take this root and duplicate it. And let me snap the pivot up there and move it to the end, and you see it's pointing, it's right at the same location as that locator. So we took the end joint and we grabbed the root and subtracted it from the end joint. So that's how we got that location. So now this midpoint is a new vector. So let's create another curve from the origin to this position. So now we have this vector. And if we snap it up to the root position, you'll see it's the exact same length from the root joint to the end joint. And mathematically what we're going to do is we're just going to multiply this by 0.5 to shrink it in half. So you can imagine we're going to get this position when we do that. So let's shrink it by 0.5, run that again, and now we have this length vector, and now we're going to add it to the root position, the root joint vector. So when we do that, we're basically going to take this new created vector from here and pop it onto the root. So now we're going to get this location right in the middle of these. So if we run this, you see we created a new point right in the middle of these two. So now midpoint is this vector. So now we're going to, you can either add or subtract it from this vector here. So let's do that. Because we want to get that length to point it towards from this midpoint, and we want a vector from the midpoint to the midjoint. So to do that, we'll take, let's see, what should we call this? Just call it pole vet position. And we'll take midpoint and subtract it from this. Let's see what this gives us. Okay, so let's actually, instead of doing this, well, so because of the order I did this in, it's going to point this way. So if I was to reverse the order, it's going to point towards this direction. So it's going to point at this mid vector. So if I just reverse these, so I take mid joint and then subtract it from the midpoint, it's going to give us this vector. And again, just to drive the point home, so we take the midjoint vector and subtract it with the midpoint vector. So let's just take this midpoint vector and snap it onto the midjoint, and you'll see it points directly at the location we just calculated. So now the pole vec position is here. So now when we add it either to the midpoint, or we can add it to the middle joint, we now have a vector that's pointing towards the same direction. It has the same direction between the midpoint and the mid joint. So we could, let's put these in parentheses. We can put it onto the mid joint vec, and let's see where that puts it. So you can see we just took this vector that was from here, and then we snapped it onto here. So now it's pointing there. So, and let's say this is too close for us and we want to push it out further, you can always multiply this. So let's do the same as before. Let's multiply it before we move it. So let's multiply by 3, for example, and create a new locator. You can see it pushed out further. So basically what it did is, if we just scale it by 3, it just scaled up the vector by 3. We multiply by 3. So now we have pushed it out further. So it's still in the same direction. So if we test this, let's create a new IK handle and a pole vector constraint. We can see it didn't snap the joints, and there's still rotation 0. But we still have the same problem as before, is if we rotate the arm this way and we do the same calculation we did before and create that, it's going to get closer and closer to this wrist, and this isn't really in an ideal location for an animator to grab the pole vector control. So to fix it, we're going to, let's get rid of all these locators. We're going to get the line between the root and the end joint again. Only this time we're going to, so let me grab this and constraint, closest point constraint. And this is sort of a new constraint, so if you're not familiar with it, it's going to create a locator on the object I selected, and it's going to give us a locator at the origin. And wherever this locator is in space, it's going to find the closest point on the object we just selected and create a locator there. So when you see this locator move, it's trying to find the closest point between this position and this curve. So basically what we're going to calculate is, so we're going to take this imaginary line between these two, and we're going to take the location of this mid vector and calculate where on this line is the closest point, and then we're going to project our line from here instead. So instead of the middle, which is over here, we're going to project to the closest point. So if we extend the arm further, and so do this, and let's snap the control vertex right there, you can see it's still going to point in a more appropriate location. So if we create a new line and then push that out, it's still going to be in a good spot where the locator expects to find the pole vector control. So let's snap this back. And another great thing about using Maya to learn these math concepts is, like, we used a point constraint to find the middle point in between these two, and now we're using another constraint to find the proper location of what we want to calculate. So we can use Maya to test our calculations and our math to make sure we know, to know we're doing the right thing. So it's really convenient that we have Maya to do this stuff. So let's go back here and figure this out. So let's just start over with these. So like I said, we want this line from the root to the end. So from root to end, we're going to get this line, and let's just name it line. So end joint vector subtracted by the root joint vector, like we did earlier. Only this time we're not going to snap it to the root joint again, because we're going to do all the calculations down here first, and when we're finished, we're going to snap it up here at the end. And we're going to get the point vector, so the point where we want to find the closest point to, which is this middle vector here. So to do that, we're going to get the mid-joint vector and subtract it from the root joint vector. And let's just create a locator there so we can see what's going on. So we took the root joint vector and subtracted it from the mid, and you got this new vector, which is this. So this is a vector from the root joint to the mid joint. So that's what we're calculating, because we want to get this from this point. How close is it to this imaginary line that we just calculated? Okay, so we got the line, we got the point where we want to do our calculations from, and we're going to create a variable called, we'll just call it scale value, and we'll take the line and do the dot product to the point. So when you're using m vectors, if you just multiply two vectors together, because of the m vector class, it'll do the dot product for you. And so we get the dot product between the line and the point, and then we'll divide by the dot product of the line with itself. So let me actually pause the video real quick, and I'm going to bring up a website to show some of this, to illustrate some stuff with this. Alright, so I'm on a website called Math is Fun, and I recommend you just type in, search Google for Math is Fun vectors, and you'll come across these pages. I recommend you read these too. I mean, just read anything you can about math, and eventually you'll start clicking on how to use this stuff. So if we scroll down, basically this is what we're doing. If this is the root joint and this is the mid joint and this is our imaginary line that we calculated, we're taking this point and we're projecting down to it, and it's going to form a right angle. And this is what we're doing when we get the dot product. So if go back and let's create, let's see if we can see this, a curve like this. Let me snap it down here, rotate it up. And then look at it from the top view. You can see, so I made a line from here to there, and I just rotated it around so it lines up with the grid. So you can see we're actually seeing what was in that diagram, where it's this closest point is actually a right angle between this line and this line here. So we can visually see this stuff with Maya. So we basically, when we got the dot product between the line and the point, we're basically getting this. And when you take when we're doing the dot product line, when you get a dot product, we take a vector and you dot product itself, it gives you the length, the magnitude squared. So if we got the length of these, which is the magnitude, and we multiplied it by itself, it's the same thing. It's just a little bit easier to just dot product itself rather than get the length and then figure it out. So we're basically projecting onto this, and then we're calculating by dividing the dot product with this dot product calculation. We're giving a scale value that we're going to scale this line by to get to this point. So remember earlier we scaled by 0.5 to get in the middle. This is giving us our scale value to get to this point here. So if, let's just comment this out, and I print this, it's giving us 0.596. So this is, instead of multiplying by 0.5 like earlier, we need to get this custom value because you don't know how far along the line this locator is. So now we got that, and we'll let's call a variable and a projection vector, and we'll take the line. And just like earlier, so we calculated this line earlier. Instead of multiplying by 0.5, we're going to multiply by the scale value, and then we're going to add it to the root joint. So we basically did the same thing as earlier, except now we're doing this calculation to get the closest point on this line and figure out the scale value to scale down this line to there. So if we actually get this, take this number and scale down by this number, you see we actually arrive at this location. So hopefully that all makes sense. If that doesn't make sense, like if any of this stuff doesn't make sense, I recommend you watch those 2 videos I provide in the description, and also just start looking for vector math tutorials if you want to learn this stuff and mess with it in Maya, kind of like how we're doing now. Like practice adding, subtracting vectors and doing dot product and things like that. For me at least, when reading and watching these videos about math, it never really clicks until I go into Maya and start messing with it. So I recommend you just mess with it. Maybe get frustrated a little bit. It's all right. Everyone goes through this process. Like no one starts out knowing this stuff. It's kind of abstract concepts. So if you just keep messing with it, Maya, eventually it's going to start clicking. You'll be able to start doing more and more stuff with math instead of doing these Maya hacks to get around your limited math knowledge, and it'll allow you to create much more like stable tools, because you're not relying on these tricks. You're relying on actual math to get to do your calculations. So now we got to project the projected vector, which will look like this. So now we're going to, let's get the length of this joint chain. So let's say this is an arm. We'll get the arm length and we'll push out this control to the length of the arm, because if we put the control too close, when the animator moves the IK handle back, it's potentially going to flip over if this intersects the control. So let's just push it back the whole length of the arm just to make sure it gives it a lot of space so the animator doesn't have to deal with the flipping. So to do that, let's go up here, and actually we can do it down here. So we'll get the root to mid vector, our root to mid length magnitude, and take the mid joint vec, subtract by the root joint vec, and we'll get the length. So the dot length will give us the magnitude of a vector. It's another thing from the mVector class. And then we'll get the mid to end length. I'll just copy this. So we're going to get the end joint vector and subtract it from the mid joint. Let's see if this is right. Yeah. So we take the mid joint, subtract by the root joint, and get the length. So we're getting this length here when we do that. And then we're getting the end joint, subtract by the mid joint, and getting that length. So we're getting this length here. And then we'll make a variable called total length, and we'll add these two. Actually, just copy these. So this is the total length of the arm. And again, we could have, since it's oriented down the x-axis, we could have just got the translate x and translate x here. But again, we just want to use math and not rely on Maya to do our calculations. So using math, this is how we get the length. Then let's create a pole vec position and we're going to subtract the midjoint from the projected vector, and then we'll get the normal, and I'll explain this in a second. Let me type this whole thing out first. Multiply by the total length, and then we'll add to the midjoint vector. Actually, before we do that, let's just see what this created. And let's do that. So let's grab curve tool again, create a vector here. So when we get the midjoint vector and subtract it by the projected vector, so we took the midjoint vector and you subtracted it from here. Actually, no, it's the other way around. We took this and subtracted it from the mid. This will give us, so if I took off this normal and take that off, that'll give us this point. And we normalize this point because if you watch the videos or already know anything about vector math, normalizing a vector will make its length equal 1. So when length equals 1, we can now scale it by let's say we want to scale it by 10 times as big. So if we normalize the vector and then scale it and multiply it by 10, since we normalized it and length is 1, when we scale it by 10, by multiplying it by 10, we know for sure it's going to have a length of 10. So what we're doing here is taking this vector and normalizing it, so we know the length is 1, and then we're scaling it by the total length of the arm that we just calculated here. So we now know it's going to be pushed out the whole length of the arm, which is what you're seeing when we with this vector here. So now we're going to take this new vector and snap it onto this end joint. So add to the midjoint vec. And let's create a pull. Let's create a locator there. And let's test this. Let's get rid of some of these. And create a new IK handle. And create the pole vector constraint. So now we created, we calculated with using vector math the pole vector position, and you see there's no rotation values. So now we can, if you wanted to give a custom length, you can always change this to like 10 to do it 10 times as big, or however big you want it to, however far you want the control to be. But in this case, I just used the length of the arm itself. And yeah, I guess we can, so that's all the math part. So let's create another function, and we'll give it an IK handle and let it calculate, grab the joints that's controlling it, and we'll have it place the pole vector from the selected IK handle. So the math part's finished. We did our calculations, and instead of creating a locator, we'll just return this newly calculated position. And let's create a new function. We'll call it get IK handle pole vec position, and it'll accept an IK handle. And we'll get the IK joint list. So we'll use the IK handle command, and we'll pass it the IK handle name, and we'll query the joint list. So before we do anything, let's so we don't need this anymore. So let's call our new function and give it the IK handle name. So it's IK handle, yeah, it's IK handle 1. It's the name of our IK handle. And let's call this pole vec position. And we'll create a locator there. Alright, so our new function we just made, we pass it the IK handle name. And here we're going to grab, let's actually comment that out for now. We're going to grab the joint list that belongs to the IK handle. So let's just print this out. And that gives us the root joint plus the mid joint. And we're going to take the root joint and grab the children because it doesn't give us the very end joint. So we're going to grab the end joint. So now we got the first two joints, the root and the mid, and we want the end joint. So we'll do IK joint list dot append, and we'll use list relatives. And we'll get the last element of the joint list array, which is mid joint, and we'll query its children and the type joint. We're going off the screen, and we just want the first one. So let's actually let's print so you see what's going on. So now we got the root, mid, and end, and you see it's in this list. We just want the one element out of the list because list relatives returns a list. So we don't want a list in here. We just want the three joints. So that's why I add the tell it to specify get the 0 index. So now we got root, mid, and end joint. And here I specify the type joint because if I remember correctly, it's going to give us the end effector when we get the children of the last joint. So if we say list the children of this mid joint, it's going to give us this and the effector. So that's why I say type joint, so we can get around that and just get the end joint. All right, so now we got the joint list of the IK handle. And we'll actually grab these and just put it in our function. And instead of specifying the names, we'll give it each element. So 0, 1, and 2. So this is root, mid, and end. And we'll get the pole vector position, and we'll use our actual math calculating function. And same thing as before, we'll give it the 3 positions. And then we'll return this. And now we can test it. All right, so now we can just grab an IK handle and say calculate the position where it should be, move the locator or whatever control you want there, and if you want to expand on this, create the point constraint from the from the control to the IK handle. So yeah, so we covered some math, and we made a useful tool from it by making a function to calculate the pole vector position, and then making another function to calculate the IK handle pole vector position. And the reason I separate these two is because what if you wanted to calculate this plane, this position on the same plane as these joints, but you didn't want to use it for IK handles and pole vectors? Now this function is a standalone function to calculate the position, and now we have a separate function if we want to use it specifically for IK handles. So hopefully that helped you out a little bit. I know this math stuff can be kind of confusing when you're new to everything. Yeah, just keep at it. You'll eventually start clicking, and you'll have a lot of fun because you'll be able to make more official tools and not have to rely on these Maya tricks to do things, and it'll make you more empowered as a technical artist or TD. Yeah, so if you have any questions, just let me know, and thanks for watching.